I'm Ritu Jugade. My hall of residence is Hall 10, room number A429. Okay, today we'll be doing chapter 3 in Griffiths, which is potentials, and the first topic in that is Laplace equation. Before that, I'll give a slight introduction to the topic. Right. So we know what are Gauss laws, right? Gauss law is and Gauss law is del dot E equal to rho by epsilon naught in its differential form. So let us write this. I am not going to write the vector sign on del. This sign I will not be writing, but E I will write because it is a vector. For convenience, I am not writing del as a vector or the vector sign. We also know that E is equal to minus del phi. I am using phi for potential. Griffiths uses V, but I am used to phi. If you have a problem, then let me know. I'll change it next time. Right. So combining these two equations, we get del dot minus del phi is equal to rho by epsilon naught, or del dot del phi equal to minus rho by epsilon naught. This del dot del phi, if you expand it in Cartesian, imagine. So you will be writing it as del by del x of I cap plus so on dot del phi by del x I cap plus so on in j and k cap. So what you will effectively get is del by del x of del phi by del x plus so on for y and so on for z, which in the end you can just write it as del square by del x square of phi plus del square by del y square of phi plus del square by del z square of phi. So because you can write it in this way, you can see that it's basically you're acting del square by del x square and so on are acting on phi. So you can define a new operator called del square. This is called Laplacian. This is also an operator, just like del is our operator, nabla, del, whatever you want to call it. Del square is also an operator, it's called the Laplacian. Right. So we can write this equation in this form. Del square phi equal to minus rho by epsilon naught. This is your Laplace equation. Right? So this is Laplace equation. Effectively, the entire electrostatics what we are learning is just a study to find the solution of this equation. If you can just solve this equation, your electrostatics is done. Our aim is to find it in every case, right? So there are some special cases of this also. So I think this is Poisson's equation. Sorry, this is Poisson's equation. However, solving this equation is not easy, and in most cases that you find, charges are located locally. In most of the space, the charge will not be there. The charge distribution will be in a small region, and you are interested in electric field which is away from the charge distribution. So if you take any small volume where you are interested, where you want to find the electric field, if you take a small volume, you don't have charge there. So this rho is actually 0 in that case. So the more interesting equation to solve generally is this. Most cases we would like to rather solve our Poisson's equation rather reduces to this, and this is your Laplace equation. Okay. So and also, as you can see, it is easier to solve because it's like a homogeneous equation. If you remember in Phi 102, when you did simple harmonic motion, the oscillator's equation was much easier to solve for homogeneous case when your RHS was 0. When your LHS is 0, you have to find a particular solution and so on. So this makes life little easier. So we'll right now focus on this Laplace equation. So the simplest case is one dimension. So we'll first start with one dimension. Let us say x for convenience. So basically this will reduce to del square phi by del x square equal to 0, and since it's only one dimension, partial differentiation is just the same as normal differentiation, so you can just write it as del square d square phi by dx square equal to 0. So since this is a second order differential equation, so we obviously need two constants to solve this and these two constants come from your boundary conditions, which we have learnt, I think, in the previous chapter. The any one boundary condition is necessary, and the fact that we're assuming that V at infinity is in this case potential at infinity, so phi at infinity is equal to 0. So your basic condition is phi at infinity is equal to 0, and one more condition from your boundary condition which you need, right? This boundary condition, as I think we have already, as is already there in the second chapter, is either you need the charge distribution on the surface that you are considering, or you need the potential on the surface. So if you have any one of these, this will give you your two conditions, and theoretically speaking, you can solve this equation. Although it's not always very simple, but it's possible to solve. So in Griffiths, there is a very simple example of a line potential, like a line function. Imagine phi of x is equal to ax plus b. Actually, Griffiths says mx plus b, so just so that it's easier to relate, I'll use m denoting the slope, of course. So in this case, we can definitely easily see d phi by dx is equal to m, and d square phi by dx square is equal to 0. So this line equation of potential is a solution of the Laplace equation. So this is a possible situation that you can have, right? This function need not always hold, right? You can have a different condition or something. It's always possible. But in one dimension, it's easy to see that this does hold. In 3 dimensions, the line may not be. It need not be a line, basically, right? Griffiths also covers Laplace in 2 and 3 dimensions, but I will not be doing it in this lecture because it's not been done in class, and I don't think it's coming in the exam either. So let's just move ahead, not waste time on that. Next we will be doing the uniqueness theorems. There are 2 uniqueness theorems in electrostatics, the first and the second, right? So we'll start with the first uniqueness theorem. This refers to boundary conditions, and as I have said here, that the Laplace equation can be solved if you have these two things. Because it's a second order differential, you need 2 conditions to solve it. The first uniqueness theorem just says the same thing, that if you have 2 conditions, the basic point of the first uniqueness theorem is that if you have 2 conditions, you can solve this equation with a unique solution of phi. So there will be a unique solution of phi if you have any 2 conditions given. In short, in simplified language, this is the first uniqueness theorem, right? The actual statement is given in Griffiths, you can refer it. It talks of if you have a given boundary conditions, and the assumption is that you already know V at infinity is 0. I have just summarized it and written it in this form, right? So the first uniqueness theorem is pretty simple. Applications are very far off, but understanding the theorem is just this much. So that's fine enough, I guess. Okay, the proof of the first uniqueness theorem, if you want, well, I don't think it's necessary for the exam, but just in case you need it, I mean, imagine there are 2 potential functions which satisfy this for the same conditions. So you can as well write del square phi 1 equal to 0 and del square phi 2 equal to 0, right? So if there are 2 solutions, then if you just look at their difference, suppose there is a phi 1 and a phi 2, you look at a phi 3, which is the difference of phi 1 and phi 2. It's easy enough to see that phi 3 will also be equal to 0. You just subtract the 2 equations, right? The reason being I'm doing this is because if del square of phi 3 is also 0, you can imagine that there will be infinitely many solutions. So the trick here to prove this would be that phi 1 and phi 2 are same, which would imply del square 0 is for obvious reasons 0. And the only way to, well, you can refer Griffith on that. I mean, it's not really important for the course. So let's move ahead. Okay. Now we will move to the second uniqueness theorem. This mainly involves conductors. So because it involves conductors, I think I'll give a little introduction on conductors. Any conductor has free electrons which can redistribute according to electric field. So once in steady state, there is no electric field inside a conductor, so E inside a conductor is 0. If there were any electric field, then steady state has not yet been reached, electrons are still moving. and once it's reached, E will become 0. Also, any conductor has no electric field inside it, so potential at all points on a conductor is same. So effectively what we are saying is, I'll just switch to the next. Okay, so if you have any conducting surface like this, this is a surface, okay? So if the potential at all points on this is the same, so any electric field outside the conductor, like just outside, will be perpendicular to the surface, that is along the normal, right? This is the normal at this point, let us say at this small surface, and the electric field will be along that. If you have a any tangential component, then there will be a potential difference between 2 points on the conductor, and which is not possible because that will mean there is an electric field over there and electrons are still redistributing, right? So that was a small introduction on conductors. Okay, the second uniqueness theorem, well, I'll read the statement in Griffith first. If in a volume V surrounded by conductors containing a specific charge density rho, the electric field is uniquely determined if the total charge on each conductor is given, right? So what this basically means is you consider any volume V, a random volume, let us say this, the volume is V, the surface being S, okay? And you know the charge density at all points in the volume. Basically you know the charge density function inside this volume, right? Then the electric field is uniquely determined if the total charge is given to you. The Griffith statements are saying if total charge on each conductor. I will talk of one conductor and then you can generalize it to several conductors. So that part is not really hard. So if you have, suppose this is a conductor, and you are given the charge density inside this conductor at every point. Basically you know all the charge distribution. Then you can uniquely determine the electric field inside this conductor, right? And because you have given rho here, if you can determine the using this determine the charge distribution here, you can determine the electric field here. That is at all points outside. So if you consider many conductors, then you consider 1, 2, 3, 4, etc. so on. And if you are given the charge distribution on the surface of each conductor, then you can overall find the electric field at every point in space. That's the second uniqueness theorem. Right. कब कहाँ तक पढ़ाएगा? हाँ, मैं इमेज मेथड है वो कंप्लीट कर लेता हूँ अभी. Okay, now we'll move on to something which is basically a mathematical trick, the method of images. Okay, so I'll call it this image method. Okay, we'll consider a very simple case, which is generally the first case ever considered in this. You have an infinite sheet conducting infinite sheet, right? Surface sheet doesn't matter much, and you have a charge, let us say for simplicity plus q, given at a distance d from the sheet, right? Your aim is to find the charge distribution on the sheet. There will be induced charges because this creates an electric field, so there will be some induced charges over here and the opposite charges will be induced over here to maintain neutrality of conductor. So your aim is to find this surface charge density as a function of this distance. I am considering this to be the origin in sorts. This is along x-axis, this is y. So your aim is to find the sigma, that is charge density, as a function of this y and z. Okay. So okay, the idea behind method of images is more important actually than the trick. So why we are using method of images is like this. This plus charge q produces some potential on this surface, on this conductor. We know that this conductor is an equipotential surface. Okay, so at any point on this conductor the potential has to be the same. Now we we have to solve this, but we don't know an easy way. So let us try and make things abstract and consider another case, right? So just forget about this for now and consider a case plus q minus q. You have two charges separated by a distance of 2d. This is d, this is 2d, right? So now there will be electric field lines. Due to both these charges, there will be a net electric field in space, right? And as we know, the electric field lines go like this, and so on. What we can find, from this charge distribution, this electric field lines distribution, is that if you take, if you want to find an equipotential surface, then you just take a line like this passing through the midpoint of these two, perpendicular to the line joining. I'll repeat. You take any line passing through the midpoint of these two and perpendicular to the line joining the two charges. Okay. So if you take any line like this and extend it to wherever you want, like infinity as first, then the potential at all points on this line is going to be the same because it's an equipotential line. You can see the electric field is perpendicular at all points here. Electric field is perpendicular like this, like this, like this. So this is an equipotential surface, right? Now, suppose the potential at this place is V, right? So let us say the potential at all points on this surface is V. Now, if I place a conductor here, if I just randomly come and place a conductor exactly superimposing on this line or small whatever line or whatever you want to call it, equipotential surface. If I exactly place a conductor superimposing this, then the conductor is also an equipotential surface, right? So the potential here will still remain V. In other words, I cannot detect that any change has happened. You will be able to detect a change or see a change only if there is some change in potential or which causes a change in electric field, and hence you see some effect is happening. But if I can place a conductor exactly at this place, then the entire conductor is equipotential surface. This was also initially equipotential surface. Potential on conductor will become V. Initial potential was also V. So effectively nothing has changed. So what you have done actually is, if you place this conductor here, you will get the same thing. So the point is that when you had this problem, you wanted the potential on the conductor. Now, if you just consider this case, you are getting the potential on the conductor. So if I change this problem into this, somehow I bring some change here and make it this, then I know what the potential on the surface is. If you have the potential and you know V at infinity is 0, by your uniqueness theorems you know that you have the charge distribution, you have everything you want, correct? So how to change here to here is all I have just changed that. There was a plus q here, I meant minus q, my mistake. Okay, so I will just continue. So our aim is to change this situation into this, and after that we know how to solve it. So how do we make this? Just by putting an image charge. Note I am calling it an image charge, or some also call it an imaginary charge or whatever you want to call it. The reason is this does not actually exist in your system. You are just making it come. Okay. So effectively what you are doing is anything on this side. Anything on this side cannot be calculated because actually there is nothing over here. No charge over here. Minus q does not actually exist on this side of the conductor. I'll again repeat, this is infinite. So this side and this side are two separate things. There is nothing like yahan or yahan se connection hai. That is not there. This is infinite on both sides. So left is an extremely different case, right is an extremely different case. You know that electric field lines are discontinuous on conductor surface. So whatever charges I put here do not effectively change anything on the right side, and whatever charges I put on the right do not effectively change anything on the left. Okay. So now I put an image charge minus q here. Again I repeat, this is imaginary. So whatever is happening on the left we cannot calculate. But we know that whatever I do here doesn't change anything on the right. So we can calculate whatever we want on the right. Okay. Now we put an image charge here at a distance d again. So if you see, this is the same situation. You see the similarity, right? I mean, it's the same situation. This is in the middle. So this conductor is lying on an equipotential surface if these two were there. So now we know how to calculate the potential just by using this. At any point here, the potential will be just the sum of the sum of potentials due to these two, right? So phi will be just phi 1 plus phi 2. Alternately, we can calculate the electric field also. So since we want sigma and we know sigma by epsilon naught is equal to E. So we will first use E because it's a simpler case. We can use E. Okay. So consider a distance r, or fine for simplicity, fine, let it be r. Consider a distance r here. The electric field for this will due to plus q will be like this. Due to minus q will be like this. Okay. Sorry, I'll draw a new diagram, probably that will make it easier. Plus q, dm, this is the distance d and d. This is the point you're considering at a distance r, and this is the electric field due to positive, and this is the electric field due to negative, right? Both are making an angle theta. By symmetry we know this. So the effective electric field, we know that by symmetry this and this components will cancel, so it will just be like this. The effective electric field at this point will be 1 by 4 pi epsilon naught q by b square plus r square into cos theta. This angle is the same theta, so into r by under root d square plus r square into 2, because this is only due to positive, so you add the negative also. So this is your E net, only magnitude again, I am not writing direction. So it is just 2qr, so 1 by 4 pi epsilon naught aside, d square plus r square to the power 3 by 2. So electric field can be written as sigma by epsilon naught cancelling, you get sigma is equal to 2 by 4 pi. I am not cancelling this 2 and 4 pi because epsilon naught can easily be replaced later, right? D square plus r square to the power 3 by 2. This is your sigma. So you have your sigma as a function of r. Note that this conducting plane is in the yz plane. Note that because of symmetry, your r as you move in the yz plane radially, that is, this is your yz plane, along any circle the charge distribution will be the same by symmetry. Because if this is your conducting plane, my hand, and you have a charge here, the distance of any point on the yz plane which has the same radius from origin, अगर ये एक सर्कल है तो पेन की रेडियस की, तो हर पॉइंट सर्कल के हर पॉइंट पे the distance between any point on the circle and your charge plus q will be the same. So the sigma will be radially symmetric along any circle of radius r. At any circle of radius r, your sigma will be the same. Only if you change your r, sigma will change. Okay. This was a relatively simple case, but the most important thing to take from this is not this answer, but the idea. How we can apply the method of images. First idea is, if you have a conductor which completely isolates one region of space from the other. So one conductor dividing entire space into two regions, two completely different regions. Then what happens in one region does not affect the other, and what happens in the second region does not affect the first. That is one very key thing. Second key thing that we need is, you have to, second key thing is like the conductor which you want should become an equipotential surface of some imaginary charge distribution. Of some of it is real, some of it is imaginary. So overall the charge distribution is imaginary. So you have to find a certain charge distribution such that this conductor which is given to you becomes an equipotential surface. Once it becomes an equipotential surface, even if you remove the conductor, there is no real change which you can see. So the answers will remain the same. That is your answer of your potential. If your potential is same, your electric field will be same, and your sigma will be the same. So these are two important keys that you have to take from here. Note that this conductor is infinite, so two independent regions, and this conductor is along the equipotential line of this charge distribution. So it's an equipotential surface, and hence nothing has changed. If you put a conductor on a non-equipotential surface, then your answer will not be correct, because you will be visibly able to detect changes due to new electric fields being produced, etc., etc. Two key points are necessary for this. Okay, I'd just like to add one more point about this, that about image method in general actually, that it's not really possible to for a given conductor you find the equipotential surface. That is really hard. Actually how this method is derived is it's derived in the reverse way. You take a charge distribution, you find what is the equipotential surface, and then say that if you have a certain surface, if you have a conductor placed there, then this charge distribution will work. It is not possible that randomly someone gives you a charge and a random shaped conductor. Like for example, I give you a charge plus q here, some random shaped conductor like this at some distance, at some given distance, and you tell me what image charges and what etc. you will take so that this will become equipotential. That is practically not possible to do. The actual thing is, they will take a certain random charge distribution, find the equipotential surface of it, and then say if you have this, if you have conductor placed over there, then you use this given charge distribution. So don't try to derive it in the reverse way. It's really not possible. Okay. I'll just give you one more case of the image problem, the image method, which is commonly used. That is for a sphere. Okay, you have a conducting sphere, and for simplicity, let us say it is grounded. Even in the previous case, you can for simplicity say grounded, because you know the potential will be 0 there. But even if it's not grounded, it doesn't matter much, and you can put another imaginary charge and it will always work. So I'll just show you once that this is grounded. Okay. So make that small change if I have made a mistake or you find I'm wrong. Right. So this is a grounded sphere, and you have a charge plus q, let us say. From the center it is at a distance r, as in Griffith. Right. Now your aim is again to find what is the potential or charge distribution at every point in the surface. So we already know how to how to proceed once you have the image charge. I'll tell you right now. I'm only going to tell you what image charge to consider so that it will become an equipotential surface. Note, logic is the same. I'll explain the logic. Right. So you take a charge minus q into r by small r. Let us say small r is the radius of this. Okay. And this charge should be along the line joining center and plus q. So these three are in one line, basically, right? If you take this, and this distance also you would need, which is r square by r. Let me just check that value. Yeah, r square by no, it's small r square by a, I think. So this distance has a value b is equal to r square by a. Right. I'll just check if these values are correct. I may have made a mistake, but these values are given in Griffiths, so that should not make much difference. The idea again involved in this is that you need to, this is grounded, so it has v equal to 0. Forget the imaginary charge for now. Let us consider what we actually have. What we actually have is this sphere, grounded, and a plus q charge. So now we need to take an image charge such that this sphere becomes an equipotential surface with potential 0. Both conditions are necessary. Sphere becomes equipotential surface with potential 0. Right? Again note that in this sphere is a conducting one, so if I put a charge here, doesn't change anything outside the sphere. Also note that by putting a charge here, I am removing my ability to calculate anything related to potential or whatever inside the sphere. Once I put the charge, you can't talk of what is inside the sphere, but you can surely do what is outside the sphere or on the sphere in this case, right? So these values are necessary for you to remember, I think, because it was discussed in class, and I think it has a strong probability of coming in the exam if they want to ask you mathematics. The entire point again will be the same, that electric field will be perpendicular, and once you calculate electric field at any point, you can easily calculate sigma. The idea of electric field again be the same. You have just two charges, so just calculate electric field using Coulomb's law. E due to positive will be 1 by 4 pi epsilon naught. Well, you know the expression, so u by r square r cap ri square, okay, where ri is this, okay, ri cap, this is this vector ri, and this is r, let us say the vector joining this imaginary charge to this point is rj, so e due to negative is 1 by 4 pi epsilon naught minus q into a by b, note minus and a by b here, rj square rj cap. Vectorially add these two, E is equal to E plus E minus, and use that sigma by epsilon naught is equal to value of this electric field. Okay, so this should give you the answer for sigma everywhere. That's it.